Hi everyone, my name is Ian Gomez, Audience Marketing Manager here at DataTorrent. Thanks for joining our architectural comparison of Apache Apex and Spark streaming webinar. Leading the discussion in this webinar is Thomas Weise, PMC member with Apache Apex. In this webinar, we will cover fault tolerance, low latency, connectors to sources and destinations, smart partitioning, processing guarantees, computation and scheduling model, state management, and dynamic changes. We will also discuss how these features affect time to market and total cost of ownership. Here are some logistics regarding the webinar. This webinar is being recorded and will be available after the session has ended to watch again and share with your colleagues who are not able to attend our session today. Please submit your questions throughout the session. You can submit your questions via the Questions tab in your console, and we'll be happy to answer them as they arise or after the presentation. Lastly, feel free to click the links and attachments below to view more relevant information after the presentation is over. With that said, I'll hand it over to Thomas. Thomas?
Yeah, hello everyone. Good morning and welcome to our webinar. So we are going to compare Apex and Spark streaming, and we will do this based on important points, and then after we have the comparison, we will go into more details how some of these things are done in Apache Apex. So first, let's start with the architectural background. So the big data processing world knows MapReduce, right? Hadoop came out, and the first processing paradigm on Hadoop was MapReduce. It was essentially a distributed file system and a processing framework that can do batch processing. And then the Hadoop evolved, and with the introduction of Yarn, the scheduling framework was broken out from MapReduce with the intention to enable different processing paradigms. In the meantime, many new use cases are also coming to the big data space that were either not on the radar earlier or not possible to implement. And many of these use cases actually rely on stream data processing. This is new because the data sources change. There's more data. It is important to process the data at a lower latency and gain basically business insights faster from the data. So a new generation of processing frameworks are frameworks that are based on processing streams. And this data can come from a variety of sources. It can be IoT sources. Kafka is very often used to feed data into processors nowadays. Still files, but also social media and other sources. But the important thing is that those are unbounded and continuous data streams that need to be processed. So batches can be processed in the same way because you can consider any batch as a stream of data, just historical data. But the opposite does not apply. A stream cannot be processed like a batch. So the other important thing is that in-memory processing was really brought to the big data space with Spark. Spark as a replacement for MapReduce enabled much faster processing for existing batch jobs with an in-memory processing architecture. But now, in the stream processing space, we need a different processing paradigm as well to handle the continuous data with processing boundaries in a stream. And we refer to those as windows. And with Windows, very closely related is the notion of maintaining state in an application. So the processor needs to understand what the data is and be able to maintain and recover the data in the event of failures to provide stateful operations such as aggregations, rule evaluations, and putting these things together, Windows and stateful processing, we refer to that as streaming analytics. So the results of such computations can be stored to a variety of destinations, or sometimes called sinks too. And just like we can take data from many sources, we want to make them available to downstream pipelines or for data visualization and so on. So those can be, again, message buses, databases, files, But it's also possible to actually serve data directly from a stream processing application to the front end, and Apex supports that as well. So the idea of taking data from where it is being processed from in memory and serving it directly to the front end, that's actually something that is new. It does not involve to move it first into another system for visualization, for example, in a real-time dashboard. That's a possible application. So let's consider a sample pipeline here, logs that are generated by user activity on a browser, by the web server, written into a file or given to a different logging sync that moves them into Kafka. And then we can have some processing, an operator in a stream processing pipeline that takes the input from Kafka. Then it can do, for example, a decompress, parse individual lines, do some filtering, and then stateful operation. We want to aggregate and then make the data available to a front end again. And in this example scenario, it could again go into Kafka and to the front end. So this is an example where you could think of a low latency processing pipeline. The events as they are generated in the front end can be processed and consumed, and as soon as an update is available, it can be fed into front end, back end for visualization. So now, this comparison is Apex compared to Spark streaming architecturally. So I borrowed these two pictures because I like them. I think they convey the message well. You have, on the left side, you have, this is Spark, right? And Spark is a batch framework. So in the batch framework, you schedule work, the work will be processed, and then the next batch can be processed. So the underlying engine is Spark's engine, which is a good batch processing framework, and it has gained a lot of popularity. This underlying engine was adapted also for Spark streaming. So to do this, the batches are made very small, 500 milliseconds, 1 second, or multiple seconds, and then the data is basically chopped into those batches and then processed as batches. Each batch is processed separately. So each batch is scheduled separately and processed. So that means we are repeatedly scheduling batches, and they are processed almost as if they were independent. This has some implications. Inherently, the architecture is stateless in Spark, and for the stream processing, that introduces a number of implications. So compared it to native streaming, so you have a pipeline that is scheduled once, and then the stream processing systems, and you got a few mentioned here, they take one event at a time, and they will process it. So just like in an assembly pipeline, the piece that is being worked on moves through the pipeline, and as soon as it has completed one stage, it's moved to the next stage. So there isn't any waiting. The events flow through a topology or through a pipeline, and they can be processed with very low latency. In addition to that, the stream processing system has the ability to maintain the state because there is no scheduling for small segments. The state can be maintained in the processor because the processor is there all the time. So there's no need to serialize the state and then load it back into the processor if you want to do a stateful operation. So that is the major difference architecturally between the two systems. Batching versus stream processing. So let's go into a few important aspects of architecture and features. So as I said, it's Spark streaming relies on microbatch. Apex, like some of the other systems, is native streaming. It's a data in motion processing system. In terms of language support, why is it important? Of course, when we build applications, we want to have the skill set available to build those applications, and both Spark streaming and Apex are Java-based. And when you can build the applications in Java, you have a wide skill set available in the market. Both also support Scala. Probably the Scala support in Spark is a little bit ahead of what Apex does, but being JVM languages, you can use Scala as well. And Spark Streaming has a few other client bindings too. The API, how do we specify applications? In Spark Streaming, it's declarative. So you have a fixed set of transformations that you can use to build an application. For example, these primitives are map and reduce or count and so on. In Apex has a slightly different approach. The underlying API is compositional, and it's that of a directed acyclic graph. You basically can compose any application logic with that DAG model, which is a lower level API. So the developer deals with operators and streams and connects the operators with streams. Being a lower level API, it gives more flexibility to the user in terms of expressing what those transformations are. It is relatively easy to introduce custom operators written against the Apex API. And it is also possible to control several of the non-functional aspects easily through configuration, and including the partitioning and processing locality and other things. In addition to that, based on the demand that we see out there, Apex also starts to provide a declarative API, which is a higher level API built on the compositional and the DAG style API, which essentially locks down some of the flexibility, but in return makes it easier for a newcomer to build the application based on a fixed set of primitives that are available. So it's a trade-off at the end of the day, but it is important that the underlying flexibility is exposed to the user, because when building sophisticated systems, and especially systems that that are long-lived and will be in production for many years, ultimately it's necessary to tune those applications and to have control over a finer grained control over what is happening. And then very often users, they will come to the point where they need the greater flexibility. So locality refers to the ability to arrange the processing so that it's more efficient, to bring it either closer to the data or closer to other processing steps. In a pipeline, you have multiple steps. Let's say a simple example, you have a Kafka input where you consume from Kafka, and you have the next operator that has to decompress messages, and then the next operator filters, like in the small example that I gave you at the beginning. So there are situations where you want to control how these operations relate to each other for better performance. For example, you may want to collocate the reading from Kafka into decompress operation in one place, because there is no need to move the data over the network in between. Or you want to move the file reader to where the data is. So Spark, being a batch processing framework and repeated scheduling, it lends itself actually very well for data locality. That means every time we process something, we can theoretically schedule it where the data is. Apex, on the other hand, is a pipeline architecture, so the data moves through the pipeline for processing. The data goes to the compute, which is also necessary for scaling out, because there's only so much processing we can move to the data. But if we move the data through the pipeline, then we can scale better. So in this approach, the ability to express locality is important. So we want to say operation A and operation B should happen in the same process or on the same machine, for example. And Apex gives you those features. You can control it even within the same thread and so on. So we refer to that as stream locality or affinity in Apex. And both of it is supported by the platform. In terms of latency, latency refers to how long it will take for an event after it was generated to be reflected in results that the user can see. That's end-to-end latency, right? There are, of course, multiple components in the processing. The ingestion mechanism or the source may have a delay. For example, if you're dealing with sensors, that they may be offline temporarily, and then the data is submitted later. But generally, if everything is online and working, it is nice to be able to process the data with low latency. And sometimes there are applications like fraud detection, for example, where it's really critical to have very low latency. So Spark streaming, giving its underlying scheduling model, will have high latency ultimately, because before we can process something, we need to wait, we need to accumulate, and then we need to schedule the task for processing. As opposed to Apex, where scheduling happened at the very beginning, it's a long-lived application. The tasks are not taken down and redeployed. Once it's running, it is just receiving the data and processing immediately. We can get very low latency. In fact, we can get a latency in the low milliseconds. And so it lends itself for those use cases where that is absolutely important. Throughput, both systems can handle high throughput. Spark streaming Apache architecture, in fact, is very much suitable for handling high throughput data, because when waiting, we can always optimize several things, right? When we process multiple events together, we can pass them together over the network. We can do some compression to reduce the bandwidth need and so on. So high latency is there in Apex. Apex has high throughput is there. Sorry. So Apex also supports high throughput through the internal architecture. It's a stream event by event, but the events are passed through the system. So in a way that that we can improve the throughput. For example, the locality that I mentioned to you allows us to improve the throughput by cutting out the need for serialization or moving over the network. And there are several things like pluggable serializers and so on that also help with high throughput. So generally, we see a very high throughput in both systems. Then scalability, Spark streaming scales to a limit. If you have to schedule many different tasks in a short amount of time, then the scheduler becomes very busy, so there's a potential limit on the scheduler. As opposed to the stream processing architecture, you schedule once and then you process for a long time, so we can say it's horizontally scalable. Of course, every system at some point has a limit, but with Apex we have shown that we can really scale out a lot, and with the partitioning schemes, we can process millions of events and internally billions of events in a second. So partitioning, Spark has standard partitioning support as it is being used for all its batch processing as well. It's definitely capable of handling large amount of data. In Apex, we have introduced a couple of advanced partitioning schemes to enable certain use cases that are otherwise hard to achieve. For example, it supports parallel pipelines that work independently, and so you can arrange multiple functions in a row, and you have no shuffles in between. And that is important to reduce the network overhead, but also to reduce the behavior on recovery. Yeah. So there's a question about
using the screen. Do you guys see the feed still?
The video feed. If somebody could confirm that you all can see the video.
It looks fine on mine.
Okay.
So that's good.
Looks good. So let's continue. So then the connector library, why is that important? So to build applications, we do not need just the engine. We also need the building blocks to realize the functionality. Applications typically need to read data from sources. They need to retrieve data from other systems for the processing, and also land data in different systems. So Spark streaming out of the box, just the Spark project has a limited set of certified connectors. There are many connectors that are maintained externally by a third party, but they are not necessarily in line, in sync with the latest release. You find the common connectors like for Kafka, Twitter feeds, and so on. but in general, it's a limited set. Also, when I look at the announcement for the latest for the upcoming Spark 2.0, the idea seems to be basically to merge the concepts of streaming and batching to overcome some of these things, but it needs to be understood that the underlying assumption of a stream having to be chopped into micro batches still remains. So I would characterize the support of connectors limited. The most common ones are there that people use, especially Kafka. But when we look at Apex, we have a very rich library of connectors and also processing functions, and supports most of the other Apache ecosystem projects. That goes from Kafka also through NoSQL databases, of course the file system, Hadoop file system, Cassandra and HBase, and so on are supported out of the box. So there is a very large set of connectors. We count probably around 75, and besides the Apache ecosystem project, you have also some of the other systems like MemSQL, of course JDBC for Oracle, things like Vertica, Golden Gate, and JDBC. So a large set of operators. These operators, they are actually maintained as part of the Apache Apex repository by the community. So when we do a release, those are certified the same way as the Apex engine.
So if you can't see your screen, go ahead and refresh, and you should be able to see the screen.
Yeah, so there's a question about can we get an example for the cascading unifier? And yes, I will get to that later. We will go through some partitioning, and we will cover it then. Also, generally, look at the attachments that we added to the webinar. There are pointers to sample code, or other presentations in the past, and other documents that should be helpful. So operability, we consider operability very important. It is an important factor to consider the ability to for time to market and to maintain a system in production. So sometimes we focus a lot of the application programming interfaces and how the developer would put together an application. We also need to consider what keeps the application running and what is the cost of maintaining a production system, especially for those pipelines that will be built to last for years and perform critical use cases. Sometimes that doesn't matter, right? When we are building experimental systems or prototyping something, then maybe we don't have to worry about those things, but ultimately there are many applications out there that have to consider the non-functional aspects and how this works from an operability perspective. So let's go through some of the important points. So the state management. State management refers to the ability for the system to maintain state and to recover it in the event of a failure. Spark streaming does not maintain state. That may sound odd, but let me explain. So Spark streaming, while processing, stores, basically takes the input as an RDD and creates a new RDD for the output. That means the equivalent of a stream is sort of a sequence of RDDs in Spark. But the function that computes the output RDD from the input RDD, as such, is a stateless function. And it is possible to make these functions stateful, but that requires the user to write code, and that is not always easy. And I would say in some cases it's almost impossible to get it right. Take the simple example of a counter. If you're counting something and we keep the count in a variable in our processing function as a member function, and now the process that hosts that code goes down. So when we have to reload it, where does the count come from? Now I could write some code that updates it every time when it changes in a database and loads it back, but that is not efficient, and it's also cumbersome to do. So Spark gives you some ability to store things into RDDs from user code. Apex takes a different approach. We are saying that all the state that you have in your computer operator can be checkpointed. And when it's checkpointed, then the platform is able to restore it in the event of a failure. So the state is managed by the engine and is automatically recovered. There's no code that the user has to write. The next generation of stream processing systems, they have those concepts built in, and we call it checkpointing. The state can be saved to different backends, and by default, that is HDFS. So there are two types of state: the state in the stream, and the state or the in-flight data, and the state in the processor. Both systems, Spark Streaming and Apex, take care of the data that's in the stream. Apex can, in addition to that, checkpoint the state that is in the processor and recover it. So recovery in Spark Streaming is basically RDD lineage. It will go back to the point where it can restore the data. So for a Kafka receiver, that would be the source. It can go back to the offset where it left off, and then recompute that RDD, and then reprocess it downstream and recompute the other RDDs per the lineage dependency. Apex has the checkpoints. It will go back to checkpoints and then reprocess whatever data was in flight. In addition to that, it does not have to reset the entire topology. It only has to reset those functions that are affected by an outage. So in an overall pipeline, you may have 10 operators. If the failure happens in the last operator, then only that last operator will be restored, and the rest of the pipeline will continue processing in the meantime. There's something called a buffer server in Apex that enables that functionality. It basically provides a restore point at every hop in the topology, and therefore incremental recovery. Incremental recovery is a feature that's unique to Apex. As far as I know, no other system today supports that. Processing semantics, Spark does exactly once processing, Apex, and we say we do end-to-end exactly once. So what does that mean? So exactly once, this is a bit misleading how exactly once is used sometimes in the documentation. Exactly once means we process an event once and only once. So first of all, exactly once cannot really be done in a distributed system. A distributed system always has the notion of reprocessing something. But we can achieve exactly once semantics. So when there is a need for reprocessing, if you can do it the same way in the same sequence and achieve the same result, and that's referred to as idempotency, then we can reach exactly once. So Spark Streaming does that for inside of a Spark streaming topology. So that means if something goes down, it will be able to recompute the state, but it does not guarantee that with the respect to the external system. Let's say we write to a database and we have done some updates. How do we ensure that we don't repeat those updates and the transactions were already committed? So that's actually something that cannot be solved by a stream processing platform. That has to be solved by the connectors that write to those systems. And that's one of the things. The value of the operator library in Apex is that those things are already pre-implemented. So by working with the processing semantics in the platform and then making sure that data is not duplicated and not lost in the connectors, we achieve something that we call end-to-end exactly once. That means by writing to files or writing to databases with Apex, you will not have data duplication and no loss of data. And from looking from the user's perspective on the results that are being computed by the application, it is exactly once. So back pressure handling is an important feature to handle short-term spikes or temporary high volumes in the stream. So back pressure is something that is of course supported in Spark, because Spark does batch processing, and in batch processing you actually have the condition of high back pressure, right? Because you have a lot of input data and it will be processed as fast as possible. So, but the control of that back pressure mechanism is a little bit cumbersome in Spark streaming. It requires some user configuration. In Apex, it's automatic. The buffer server, when it fills up the configured amount of memory, it will start to spool to disk, and it will also block the consumer of the data to the speed at which it is writing to disk. So back pressure naturally builds up to the source, and the processing slows down to the slowest unit in the processing pipeline. Elasticity refers to the ability to adjust the processing resources to the needs, to the processing needs. So when we have a lot of data to process, we want to allocate more resources. When the high load condition goes away, we want to scale the resources back. It's possible in Spark. Because it's scheduling, it can repeatedly reevaluate the need for resources and schedule accordingly, but it's exposing limited control to the user. Apex also supports elasticity with dynamic partitioning. And in addition to that, it provides the user full control over how to make those partitioning decisions and also how to distribute the state. We will cover that a little bit later. So let's quickly take a question here. Does Apex has functionality similar to Spark mlib, Spark SQL? So Apex comes from the processing, stream processing side, and our operator library provides functions, provides the adapters to build such pipelines. We don't currently have the support for SQL. SQL is on our roadmap, and we also don't have a machine learning library inside Apache Apex. But we are actually building we have recently added the underlying capability for iterative processing in Apex, and we are working on integrations with other community projects like Malhar to provide the machine learning algorithms on top of Apex in the future. So how is checkpointing in Apex different from Flink? Actually, it's very similar. When you look at the documentation, there is the notion of a checkpoint barrier flowing through the topology, and then the state of the operator being serialized. So checkpointing is very similar to that in Flink, but the recovery in Apex is very different from recovery in Flink. Flink has to reset topology on any failure. Apex does incremental recovery. So RTS 4.0 is not released yet. It's probably going to be out in a few weeks, and the current download page is 3.3. That's correct. So look for announcement for RTS 3.4.0. The slide deck will, of course, be shared. So I will take more questions later and move on here. So we have the ability to do dynamic topologies in Spark streaming now. The topology is fixed when you submit the job. Of course, you can resubmit the job to change the topology, but in Apex, you can change the topology as the application is running. So there's an ability to add operators and remove operators and modify the topology while the system is running. Support for security, Spark supports Kerberos, and Apex does support Kerberos as well. In addition to that, the front end in the DataTorrent RTS Community Edition reports several other authentication mechanisms besides Kerberos. And it also supports role-based access control for the user to manage the applications. That's available in DataTorrent Community Edition, and DataTorrent Community Edition is available for download for free. You can install it on any of your clusters. Support for multi-tenancy. Spark streaming depends on the cluster manager for that. So if it's running on Yarn, then we have multi-tenancies through Yarn. If it's running on Mesos, we have whatever Mesos supports. Apex was built for Yarn. It natively integrates with, uses Yarn. And with the Yarn support, it provides the full isolation and in a multi-user environment. So the DevOps tools in Spark are basic, and there are tools available, but the best tools you get when you use the Databricks cloud hosted environment. Apex has the tools provided through DataTorrent RTS, which I said you can download and you can install anywhere and use for free as the community edition. In addition to that, Apex provides the REST API, and so basically you can build your own monitoring tool against the REST API as well. Some of our customers have done that. So generally, the management console within the DataTorrent community edition is very rich featured, and it provides a lot of functionality, including looking at system metrics, looking at the log files from the different containers without having to go into individual nodes in the cluster, looking at the logical and the physical plan, also changing properties at runtime. All of these functions are available in the management console. I think it's a very good offering, and generally the ops people, they love it. They also love the DataTorrent RTS installer that makes it really easy to install on an existing Hadoop cluster. So some of the Apache Apex features to recap: it's in-memory stream processing platform. It was developed since 2012, and it became Apache top-level project in April. It provides an unobtrusive Java API to express custom logic, and that's important. I mean, how easy is it to actually write custom business logic? In Apex, you can do that. Writing an operator is relatively easy for a Java programmer. It is a scale-out architecture. It's distributed in parallel. It supports high throughput and low latency, as we discussed. It supports windowing. So inside the stream, you need boundaries at which to perform aggregation operations, and so windowing concepts are there, and this is an area where we are actually expanding. Besides basic processing time windowing, some of our operators support event time windowing. We are working on more generalized concepts to expose more of these windowing concepts to the user in a more easy-to-use way. Apex features reliability, fault tolerance, and operability. It is Hadoop native, and so it runs on any Hadoop 2.x cluster with all of the distros that are out there. It supports the performance optimizations for compute locality and affinity, and then it supports dynamic updates and elasticity, as I mentioned in the comparison. So quick question here, what kind of ML library is in the Apex? There is no machine learning library in Apex today. Apex has an integration with R that's available from our Malhar library, but as far as native machine learning library, Apex doesn't have that. It's also not on our roadmap to develop something like this within Apex at this time. Rather, we are looking forward to integrate existing machine learning libraries that are tailored for distributed processing, and we want to integrate them. So, for example, as I said, we are working with Samoa, and we are actually open to other suggestions on which libraries that can run on Apex as an execution engine. So our goal is to leverage existing know-how and knowledge in machine learning, and then use Apex as the execution layer. Oh, good, we got that. Right, so let's look at the platform overview quickly. So we got Yarn and HDFS underneath as the base. It can be on hosted. It can be on a hosted environment like Amazon, or it can be on-prem with all of the common distros that are out there. Apex has two components that are released separately. One is the stream processing engine, the runtime, and the other one is the operator library. And they are moving at different speeds. The operator library generally changing faster than the engine, and we are also watching for backward compatibility. You're using those two pieces, the library and the engine, basically to build your streaming applications. And then on top of that, DataTorrent provides some value-added tools, the management console that I mentioned already, but also the application assembly without Java coding and data visualization, which can be used, for example, for real-time visualization of data as it is being computed in a dashboard that lets you configure widgets. So it's an easy way to build a dashboard. Could be a real-time dashboard or can also show historical data. But it's basically serving data from the application as it's being computed versus relying on external data sources. And the Apex engine exposes the REST API that can be used to build tools around it. The DataTorrent tools that are running on top, actually, they use the REST API to perform all of their functions. The Malhar operator library contains all of the connectors that I mentioned earlier, and then also operators, compute operators, to do things like parsing, filtering, aggregation, and so on. The application development model is set of a directed acyclic graph. So essentially, you're connecting the operators that you have. You're building up, we call it also a logical plan. You're taking the operators, you're connecting them through streams. You can express any processing logic with that paradigm, parallelism, sequence, and arbitrary complex applications. So an operator takes one or multiple input streams, and then it performs some computation, and it can emit on one or multiple output streams. And these operators can be either pre-built operators from the Malhar library or operators that you build and that contain your custom business logic. And operators have a simple processing model. It's single-threaded, and I already mentioned the checkpointing. So basically, there's an environment provided to the operator. The container environment provides the fault tolerance and the synchronization. So as an application developer, you don't have to worry about those aspects. So yes, this is a good question. I mentioned earlier iterative processing. That would be hard to do without supporting cycles in the graph. Yes, we do support cycles in the graph. That's a feature that was recently added where the output of one operator can be fed back into an upstream operator for processing. And this is how you can run machine learning on Apex, for example, or use it for auto signaling purposes. In batch processing too. For the windows first. So the streaming windows, that's an engine concept. Essentially, we are injecting control tuples periodically into the data stream, and those control tuples, they will be used by the engine, but also can be used by the operator developer to perform periodic logic. So one application of this is the checkpointing. So some of the windows are marked boundary. So this is how we get a consistent state snapshot, and then we can use at any point in the DAG as an incremental recovery those state snapshots recover an operator. The callbacks at the begin and the end window, they are also available to the operator developer. So you can perform functions. For example, let's say you want to do some partial aggregation every so many windows. You can implement this in an end window callback, or you want to clear out some state or do some other optimizations. So those callbacks, begin window, end window, are available to the operator developer. So important to notice that the windowing does not introduce any artificial latency. It's not if the operator logic is I take an event, I do some processing, for example, filter, right? I decide by looking at a field whether this passes or not, then and emit immediately. There's no latency being added due to the windowing concept. It is something that is just control markers in the stream that can be used but don't have to be used. We are working on a more unified support for event time windows and session windows and so on. Those concepts will actually be built on these underlying streaming windows because there's always a need to evaluate the state at a certain boundaries, and these So here's an example. I'm going to skip that quickly, but this shows how in Apex you can actually do event time processing, we call it dimensional computation. So when you look at the T field in the data tuples, you can actually see how these events are processed, and there's no assumptions about the arrival order of the tuples. We are looking at the time field. We find out to which windowed state it belongs, and it can be updated. So below the arrow, you see the state. Above the arrow, you see the data stream. I can change the order of these data tuples any way I want. I will still arrive at the same end result for the aggregation. So this is important because in Spark streaming, because you don't have the state or you have to manage the state by yourself, you kind of rely on the order in which the tuples arrive in the stream, and that's why it's typically processing time-based functionality that you can implement, unless you write your own state loading and saving, which adds overhead because to do this for every batch, it's really expensive when you have a lot of small batches. Okay, so there's a question about who is responsible for injecting the control tuples. So the control tuples are injected by the platform. Each source or input operator, we call them, has a window generator. That window generator will periodically inject these tuples into the stream, and from there, they are transported through the entire topology. So because you can have multiple sources, right, there's also the notion of synchronizing on a window boundary. So when a given control tuple arrives and you have multiple inputs for an operator, it's possible that one stream moves faster than the other. So the end of that window is the point where actually the synchronization will occur to bring the streams in sync, because we can only guarantee consistent processing results if the processing happens according to the window boundaries. So yes, the tuples are injected as the source and traverse the entire topology, and it's handled by the system. So scalability support, Apex handles large amount of data and it can arrive at high velocity. The architecture to handle that is pipeline and partitioning in conjunction with back pressure support. So partitioning means that we can run the same logic in multiple processes, and each partition then processes a subset of the data. And this is available out of the box. Apex supports different partitioning schemes, and we're going to look into some of those now. Important to note that partitioning is separate from the processing logic, so the partitioning decisions and how the state is being transferred is kept separate from the logic that the user writes, and that enables basically to also change partitioning schemes and how you partition without rewriting the application. So here's an example, simple case, a source, an operator that processes something labeled as 1, and then an operator that maybe outputs the data somewhere. We want to partition the operator that is 1. For example, we find out it's a bottleneck, it needs more resources, so we can specify just for that operator what should be the partitioner. We can assign a default partitioner and tell it we want 3 partitions. Very simple case. Now that we can process the data in parallel, we can handle a larger volume of data, but we also need to think about how we can bring the data back together if the next operator requires that. So that piece is called a unifier. It's a mix between what you may know as the combiner and user in MapReduce, so it takes the input from multiple upstream partitions and understands how to combine them. And actually, the logic in the unifier depends on what logic the upstream operator performed. It's different for let's say a sorting or top-n operation than it would be for a filtering operation. Filtering operation does nothing to be done except passing on the tuples, but for an aggregation stateful operation, the unifier actually needs to keep track of the state and correctly merge it. So N by M partitions, that's what you all know. That's probably, or most of you know, from systems like MapReduce and Spark. We perform a shuffle, right? So we don't want to send all data into a single unifier and that become the bottleneck. Instead, we have multiple, and we do some key-based distribution to the next operator. So each unifier has to only take accept part of the stream, but from all upstream operators, and then hands it off to the next operator. So that's the shuffle operation, which Apex supports. There are more advanced partitioning schemes. So if we take parallel partition as an example, so here we say we have 5 operators, and we want to process 3 of them in one pipe without any intermediate shuffle, because shuffle is expensive. So we can say 1, 2, and 3 should be in a parallel pipe, and how many of those parallel pipes should be there. And after 3, then we merge the outputs and pass it on to 4. Now, you can imagine if you don't have operator 4, then there's no need to merge at all. That opens up for an interesting set of use cases where you don't want data to be merged, but you want to have processing to happen independently. And also, when there's a failure, you want that failure not to affect all the other pipelines. So let's say I had multiple of those parallel pipes and one fails, the other ones, they can continue to process, they are not affected. So one use case is I want to ensure an SLA, right? I need a certain processing time maximum. So that can only be done if we have parallel processing and the assertion that when a failure occurs, the rest of the DAG is not affected. And the Apex supports that with the incremental recovery and the parallel partitioning. So then cascading unifiers, if you have an aggregation operation and you have passed a lot of data through the stream, you may want to arrange the unifiers in multiple levels to handle the amount of data without running into a network interface bottleneck. That's supported as well. We call it cascading unifier in Apex. And then dynamic partitioning is supported. We can say that we want to change the number of partitioning at runtime. It's possible to evaluate stats either from within the system or external stats and make the decision that we need more resources, then trigger the partitioning and basically create more partition. It's a stateful operation. It will retain the state of the partitions, and this can be used for scaling up and scaling down. An example for an externally driven partitioning is Kafka, actually. The Kafka operator looks at the partitioning in Kafka of a given topic and then creates the operators accordingly and distributes the consumers over them. There are some details about dynamic partitioning that you can look at later. So basically, the decision to partition yes or not is separated from how we partition. So there's something called a stats listener that makes the decision. It's a pluggable component. It can contain custom logic. It's also possible to write the code for the user how we partition, how we take the state of the existing partitions, because everything is stateful, and how we distribute it over the new partitions. And then the engine handles all of the rest of it to basically modify the plan, rewrite checkpoints, undeploy the affected operators, and then release or request new computer resources and redeploy the partitions. So that's all handled by the engine with maximum control given to the user as to why we partition or when we partition and how we partition. And these interfaces are all exposed in the API with default implementations. Fault tolerance Apex is fully fault tolerant with operator state being checkpointed. As I said, it's asynchronous and distributed, and the sync for the checkpointing is also configurable. By default, it's HDFS. Yarn is being leveraged to detect process failures, and then the logic what happens after a failure is provided by the Apex platform, handling the state of the operators and so on. The incremental recovery supported through the buffer server, and the application master. Apex has an application master. The application master is basically just there to observe the processing. It's not involved in the processing, but that state is also checkpointed, because if we allow for dynamic plan modifications, then we also need to be able to restore any of such changes when the master fails. So the buffer server between two containers, an operator that produces data gives them to the buffer server. It's an in-memory pub/sub mechanism, no disk writing, very fast. The downstream operator subscribes to the buffer server. Think of it like in-memory Kafka, and the buffer server is hosted with the operator that produces data. That's the component that will handle the back pressure and also facilitate incremental recovery. And then a recovery scenario, very simple. We are counting data. We have a sequence of data tuples that we process. Let's say we have a state that we checkpointed once we counted till 7. It's written. We have a failure that occurs afterwards. And then the platform will take care of bringing back the appropriate checkpoint, rewinding the consumer to the appropriate point in the stream, and then reprocessing the tuples. So it's the state snapshot, the ability to replay in an idempotent manner that makes the computation in Apex topology exactly once. So exactly once is at least once plus idempotency, plus the transactional mechanisms or whatever other mechanisms the downstream or the external system provides. Don't have time to go into the details, but there are detailed presentations about fault tolerance out there on the SlideShare link that is in the attachment of this webinar. So I'm going to skip this as well, but as I said earlier, end-to-end exactly once refers to ability from the user's perspective that the system, even when integrated with external systems, doesn't lose or duplicate data, and it's correct its computation. This is an example from the pipeline builder or application builder in the DataTorrent tool, where you can connect operators without the Java code. And this is the monitoring console that's part of the community edition. You can basically see the stats there. You can see the topology. You can observe events for operators when there are failures. You can see them here. You will see all the processes on which machines they are allocated, and you can view the log files from here. You can see the progress of the topology, number of events processed, the current window IDs. You are also able to do some dynamic changes like property change through this interface, as well as, of course, uploading the applications that you have built, launching them, and so on. So this is a comprehensive tool for operating Apex applications. As an example of a physical plan, here you see, compared to the previous one, you see the individual partitions. And then finally, an example for the data visualization dashboard that you can build. And then use cases. After the presentation, feel free to go back to the slides and look at some of the use cases that are implemented with Apex in the IoT or online advertising space and the business value provided. So one of our customers is GE, and they use Apex for computing data from their IoT sources. And another IoT use case. And so we have a few minutes left for Q&A.
Okay, so I know we're running out of time, but if you guys want to stay on for 2 more questions, we'll go ahead and take them. There's one about partitioning. Are the partitioning schemes specified by the user application, or is it automatically chosen by the platform?
Yes. So as I said, the API, the Apex API, gives you full flexibility. So it's necessary to control what the application does to provide that API too. So the partitioning scheme is not automatically chosen. You choose, right? It's configuration. So for example, you can set an attribute that says 2 operators should be parallel partitioned, or you will set an attribute by just setting the count for individual operators. You configure them for shuffle. This is all configuration driven.
Great. The next question is, can we see the example code for each partitioning and unifier example?
Yes, I'm gonna make. Do we have an ability to make something available after the webinar?
Yes, we could upload links.
Yeah, so we can upload. We can add another attachment. The presentation links are there that actually contains code for that. So we will provide you the link after the webinar.
Cool.
So here are the resources, and they are also as link on the webinar attachments. So we have a look at our Apex community website. The mailing lists are there to follow what we are doing. You can follow us on Twitter. All the important updates go through there. Then we have meetup groups in different locations in the world. Have a look at the upcoming topics, then example applications in the example repository, and also other SlideShare presentations that go into the depth for some of the things like the partitioning or the fault tolerance. Those topics are there, and also for use in IoT workspace. There are actually, for the use cases, detailed presentations from GE, from Silver Spring Networks, and also Capital One that you can look at how Apex was used there.
Awesome. Thanks, Thomas, for that great webinar. So this will conclude our webinar. If you'd like more information about Apache Apex or would like to join our growing meetup community, again, feel free to check out the links below. We'll be sure to upload the slides after the presentation is over. Thanks, everybody.